This is video 1 of Chapter 6 from your operating systems textbook. We'll be taking a look at deadlock and starvation as we continue our discussion on concurrency. In this video, we'll be covering section 6.1, Principles of Deadlock. So, when we're talking about deadlock, we're talking about the permanent blocking of a set of processes that either compete for system resources or communicate with each other. Now, that set of processes is deadlocked when each process in the set is blocked, awaiting an event that can only be triggered by another blocked process in the set. Now, deadlock is permanent because none of the events is ever triggered, so none of these processes that are deadlocked can ever make any kind of progress. And unlike other problems in concurrent process management, there's no efficient solution for deadlock in the general case. Now, I think the best way to understand what deadlock means is to take a look at an example. So for this example, let's take a look at 4 cars that all want to go through an intersection. Now, the cars are analogous to the processes that are trying to move forward and do what they need to do. And the 4 quadrants of the intersection that you see here labeled A, B, C, and D are the resources that each car needs. Now, to get through the intersection, the cars need these resources in a certain order as follows. Car number 1 needs A, then B. Car number 2 needs B, then C. Car number 3 needs C, then D. And car number 4 needs D, then A. So what would happen if all 4 cars decided to ignore the rules of the road and try to go through the intersection all at the same time? Car number 1 would get access to resource A, car number 2 to B, car number 3 to C, car number 4 to D. So far, so good. But remember that each car needs 2 resources to get all the way through the intersection. Now, since each car is locking up one resource, assuming that none of the cars can back up, we're stuck. None of the cars can go forward because they're blocked by another car. Another car has locked the resource that each car needs to continue on. So this illustrates what deadlock means. None of the cars can make further progress through the intersection. And when we're talking about processes, this means that no process can make any kind of forward progress and can continue processing. Now let's look at a depiction of deadlock involving processes and computer resources. This figure, which we refer to as a joint process diagram, illustrates the progress of 2 processes competing for 2 resources. Each process needs exclusive use of both resources for a certain period of time. The x-axis represents progress in the execution of P, and the y-axis represents progress in the execution of Q. The joint progress of the 2 processes is therefore represented by a path that progresses from the origin in a northeasterly direction. For a uniprocessor system, only one process at a time can execute, and the path consists of alternating horizontal and vertical segments, with a horizontal segment representing a period where P executes and Q waits, and a vertical segment representing a period when Q executes and P waits. The figure indicates areas in which both P and Q require resource A, which are upward slanted lines in the diagram. Both P and Q require resource B, which is indicated by downward slanted lines, and both P and Q require both resources. Because we assume that each process requires exclusive control of any resource, these are all forbidden regions. That is, it's impossible for any path representing the joint execution progress of P and Q to enter these regions. Now, our figure shows 6 different possible execution paths. Let's take a look at them one by one and talk about whether they're going to work out or not. In path 1, Q acquires B and then releases B and A. When P resumes execution, it will be able to acquire both resources. In path 2, Q acquires B and then A. P executes and blocks on a request for A. Q releases B and A. When P resumes execution, it will be able to acquire both resources. Now in path 3, Q acquires B and then P acquires A. Deadlock is inevitable here because as execution proceeds, Q will block on A and P will block on B. In path 4, we also have a situation where deadlock is inevitable. P acquires A and then Q acquires B. And again, as execution proceeds, Q will block on A, and P will block on B. In path 5, P acquires A and then B, Q executes and blocks on a request for B, P releases A and B, so when Q resumes execution, it'll be able to acquire both resources. Finally, in path 6, P acquires A and then releases A and B. When Q resumes execution, it'll be able to acquire both resources. We refer to the gray shaded area as a fatal region. Now this applies to paths 3 and 4, and if an execution path enters this fatal region, then deadlock is inevitable. We simply can't avoid it. But note that the existence of a fatal region depends on the logic of the two processes. So deadlock is only inevitable if the joint progress of the two processes creates a path that enters that fatal region. This figure, on the other hand, shows a situation in that, regardless of the relative timing of the two processes, deadlock can't occur. Now, as we see here, the joint progress diagram can be used to record the execution history of two processes that share resources. In cases where more than two processes may compete for the same resource, a higher dimensional diagram would be required. The principles, though, concerning fatal regions and deadlock and when it will and will not occur remain the same. Now, we keep talking about processes that want to use resources, so let's take a moment to talk about those resources, and specifically let's take a look at the categories that a resource can fall into. First, we have reusable resources that can be safely used by just one process at a time and is not depleted by that use. So processors, I/O channels, memory, files, databases, etc. These are resources that can be used over and over again. So even if they can only be used by one process at a time, it's not as though they go away after being used. Consumable resources, on the other hand, can be created or produced and destroyed, which is when we say they've been consumed. So interrupts, signals, messages in information in I/O buffers, for example, these are consumable resources that can actually be destroyed. So here is an example of deadlock involving reusable resources. We have two processes here that compete for exclusive access to a disk file D and a tape drive T. The programs engage in the operation that you see here in the figure. Deadlock can occur if each process holds one resource and requests the other. So, if the multi-programming system interleaves the execution in this way, P0, P1, Q0, Q1, P2, Q2, we run into a deadlock situation. The reason that we have a deadlock situation is that at step P1, process P locked resource D, and at step Q1, process Q locked resource T. So when process P requests access to T at step P2, it can't get it because process Q has it locked, and when process Q requests access to resource D at step Q2, it can't get it because process P has it locked, so neither process can make any more progress. Now that we've seen an example of how deadlock can occur using reusable resources, let's take a look at how it can happen using consumable resources. Consider the following pair of processes in which each process attempts to receive a message from the other process and then send a message to the other process. Deadlock occurs if the receive is blocking. So if the receiving process is blocked until the message is received. Once again, a design error is the cause of this deadlock. Such errors may be quite subtle and difficult to detect. Furthermore, it may take a rare combination of events to cause the deadlock, so a program could be in use for a considerable period of time, even years, before a deadlock actually happens. This is table 6.1. It appears on page 266 of your operating systems textbook and summarizes deadlock detection, prevention, and avoidance approaches for operating systems. Please take a look at this in your book, study it, and make sure that you understand all the schemes, advantages, and disadvantages of the various approaches. So let's talk about the conditions under which a deadlock can occur. We have mutual exclusion. Only one process may use a resource at a time, so no process can access a resource unit that's been allocated to another process. Hold and wait means that a process may hold allocated resources while awaiting assignment of other resources. And third, we have something called no preemption. That means no resource can forcibly be removed from a process holding it. Now, in many ways, these are good things. These are conditions that are desirable. For example, mutual exclusion, as we talked about in our last set of videos, is needed to ensure consistency of results and integrity of, say, a database. Similarly, preemption should not be done arbitrarily. For example, when data resources are involved, preemption has to be supported by a rollback recovery mechanism, which restores a process and its resources to a suitable previous state from which the process can eventually repeat its actions. So the first three conditions here, mutual exclusion, hold and wait, and no preemption, are necessary but not sufficient for deadlock to happen. For a deadlock to actually take place, we have to have the fourth condition, which is circular wait. That means a closed chain of processes exists such that each process holds at least one resource needed by the next process in the chain. Now, that fourth condition is actually a potential consequence of the first three. So, given the first three conditions exist, a sequence of events can occur that lead to an unresolvable circular wait. The unresolvable circular wait is, in fact, the definition of deadlock. The circular wait listed as condition 4 is unresolvable because the first three conditions hold. So, the four conditions taken together constitute necessary and sufficient conditions for deadlock. So, now that we know what deadlock is, how do we take care of it? How do we deal with this problem? Well, there are three general approaches. We can prevent deadlock, which means to adopt a policy that eliminates one of the conditions. We can avoid deadlock, which means to make the appropriate dynamic choices based on the current state of resource allocation. Or we can detect deadlock, to attempt to detect the presence of deadlock and take action to recover. And that is what we'll be dealing with in our next video. So that's the end of video 1 from chapter 6. And again, in video 2, we'll be talking about prevention and avoidance of deadlock. And then in video 3, we'll talk about detection and recovery.